Okay, so we started talking about analog to digital converters, and we said that one of the methods is to use counting A to D. The idea here was to give all the values, starting from this number 0, 0, and 0, 1, and then this one, and then related values are compared, and with the unknown voltage, and if it is below that value, it's okay. When it in this comparator, if your D to A output goes beyond that, then that's the critical point. So after this, we make a decision. I mean, there are two things here. Depends on how we define the value. If 4.5 is converted to this like 4, then the decision is going to be just the one before this next one. So if we say that 4.5 will be counted as 5, then we will be selecting this one as the output. But normally we select this one as the output, and this is just to be consistent with the evaluation of the number. I mean, if you remember when we said here, what is this code, what is the output, and then code, related code, and here the definition was, to find the value here, like this one, we multiply it with this, and the code would be this number. Anything beyond this was counted or truncated. So that's how we define the numbers. But the definitions might change, and also we might do some offset. When we put an offset, then things will be different. So in this example, like this was the case where it was only 3-bit, and then we said 4.5 volt, and then what would be the equivalent digital conversion of this. So sometimes we add an offset just to define this and find this correctly. So when we have 0, 0, for example, the output of this 0, 0 is started from maybe the voltage of 1. So therefore this definition is going to be corrected. So that means we apply extra least significant bit addition to that value to make this correction conversion. Instead of selecting this one, then we select the previous, instead of previous one, the next one is going to be selected. So similarly here, if you have this kind of, let's say, reference 1 volt, and then let's say this Vn, and then we have 4-bit A to D. So the expectation here is to find the value as you know, the definition was for the 4-bit, we have 2000, for 4 bits, what is the bit number? 2 to the power 4. So this is 16, okay? So there might be 16 maximum of the signal. So this is the unit is here is the weight of this is you know, the voltage value corresponding to this is going to be this much, and then it's going to be 2 to the power 0. The weight of this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So, you know, here, if you see this one, of course, this is 15, right? So in order to determine the value here, what we do is 0.6 divided by 1 volt and times 16, right? So if you do this, this is going to be how much? Yeah, so this will be the value, and so this is going to be this will be the value. Is that correct? 10.6. So
9.6, I think.
9.6, sorry. Yeah. So this will be 9.6. That's why the value should be 9, okay? So as you remember, this is 2 to the power 0, this is 2 to the point 1, 2 to the point 2, and 2 to the power 3. So 9 is going to be 8 plus 1. So that's why this is 8 plus 1 is the 9. So the conversion is going to be 9, not 10. So if we divide these values and then say that 0 is 0 and this one is this much, you know, when we have 0.6 volt, this is somewhere in between here. So just the one before this is the result, okay? So what we do is then start counting, and then as soon as we pass, the number just before we pass is going to be the equivalent number, digital representation, okay? So in order to find this value, we had to wait. I mean, counter is going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, 0 was 0 anyway. So it's going to be at least, you know, 9 times counting, or maybe 10 times in order to find that properly. But you know, the counting is going to be like 10 TC. So it takes a lot of time. So we said that an alternative is developed to find that value, and the alternative is to compare that number with you know, half of first this one, half of full scale, and then if it is less, then we add the number here. If it is less, then we compare it with the you know, half of that half, and then that's how we we say? I mean, if the number is larger, if this is the case, then we compare with this one. And if it is larger, we compare with this one. Okay, so what we do is we fix the Vx. Vx is fixed here. Vx is fixed, and then we change this comparing data. But this comparing data is selected smartly, and then you know, we first look at with the first this data. So DAC is going to have this data, and then you know, depending on if it is larger or less, then we go and then select this one. So there is an example here. Again, like, you know, what can we do to make comparison and how we can find that. But the bottom line here is that the maximum conversion time is going to be n times TC instead of 2 to the power n times TC. So this is a much better way to find the value. So here is, you know, the same example. We can look at the value, how to compare. You know, first thing, we will be comparing the number. Is Vn going to be larger than or smaller than like this value? Okay, so this value is going to be comparing what is the voltage equivalent of this value. Voltage equivalent is Vref divided by 2, so that's going to be equal to 0.5 volts. Okay, now if we know that this is Vin is larger, since Vin is larger than 0.5 volt, then we make the comparison with you know, 1, 1, 0, 0. So what is that value? That value is 0.75. Why? Because this one is 0.5 volt, this one is 0.25 volt. So that's the value. So we make the comparison with that. And then we realize that it is less than this. Okay, so Vn is less than 0.75. Therefore, we start comparing it with 1, 0, 1, 0. Okay, so then this is going to be how much? 625, 0.625. It is also 0.6 is less than, or Vn is less than this. Vn is less than this, so therefore we make the decision, and then we say the number should be 1, 0, 0, 1. Okay, so, and that is going to be the final result. Okay, so this is the decision, how it's made. Is it larger or smaller? So that final bit is going to be decided. So the result is going to be 1, 0, 0, 1. How many cycles required to make this decision? 1, 2, and 3, and then maybe the fourth one, you know, for this to make a decision. So you know, the conversion time was 4 times TC or n times TC, and this is fixed. Okay, independent of the number, whereas in the previous one it was changing depending on the value. And so this is very you know, preferred way of determining the value, and that's how we make you know, the decision. So for the successive approximation, there are, you know, some other, I guess, let's see, what is the slide? Why do we have a slide? You know, in the time cycle, I guess it's explaining it. It's the same thing, like, you know, cycle 1 comparing with this 0.5, and cycle 2 comparing with this one, you know, 0.75, same thing, and then this one, and then the comparing with this one. So that's the final output is determined. The same thing is explained maybe. And this SAR ADCs are very popular. There is one other type of ADC. It looks like this one. I wanted to explain this to you, but maybe I don't want to, you know, spend time right now. But note that there is another approach called algorithmic ADC, where VREF is kept fixed and the input Vn is, you know, Vn is changed to determine the number. Okay, so for example, in here, let's say that this is the case, like VREF and Vn. Okay, so what you do is you multiply you compare Vn. Let me remember how this was done. You compare Vn with ref. Okay, so VREF is fixed. So okay, so this is how we do. We multiply Vn by 2. Okay, 2 times Vn. We compare it. Is it larger than VREF? For example, here 1.2 is larger than 1 volt. So the most significant bit is defined as 1 because it is larger. Okay, so then what we do is, if it is larger, we subtract VREF. Okay, 2Vn minus VREF is decided and then multiplied by 2 and compared with VREF. Okay, so what is that? Like 0.2 volt. Is 0.2 volt, 0.2 volt times 2, is it larger than 1 volt? No. Therefore, the next bit, I mean, this bit was 1, the next bit becomes 0. Okay, so let me do this. Okay, so after that, we don't, this time, if it is 0, we don't subtract this. We just take that 0.4 and then multiply that by 0.4 with 2, and then the result is 0.8 volt. Is it larger than 1 volt? No. So then the next bit is going to be 0. Okay, and then we take 0.8 volt multiplied by 2 and then, that's going to be 1.6 volt. Is it larger than? Yes. Therefore, the data is going to be 0. So therefore, the same result is obtained by playing with V in. Okay, so if you do this, you will be finding that, and I like this approach, and I used it in my PhD thesis, and the chip that I designed. I used this kind of algorithmic ADC, and this is not included in the course material. Okay, so not included in EE312. Okay, so you are not responsible, but just to let you know that this was an interesting also method to determine the value. Okay, I couldn't hold myself, to explain you this. It's just another way of calculating things. Okay, so there are some other famous methods, and then highly preferred methods. The approach is called single ramped ADC. This is quite similar to counting, the counting converter. So instead of here, instead of using a DAC and a counter and n-bit counter, we use an analog ramp voltage generator. So again, here the idea is to put here as a comparator this one, and then Vx, and this voltage is, how are you going to generate this voltage? We just have an integrator, for example, and then start the voltage from 0 volts, and then increase that up to V full scale. Okay, so meanwhile, the point where it passes that Vx, and then we make a counter, and then counter counts this. Let's say this is Vx voltage. Counter finds that value. From the counter value is going to be giving you that value. So this circuit is connected like that. Some details are shown here. So I'm going to tell you about this. So let me. I'll be talking about this. Hold on a second. So So here is the idea. As you know, this is going to be, if you have a voltage source here, a current, is going to be in this direction. So there is an extra element here, but this whole thing is to create an output voltage. So this is going to be out. As the current, the voltage is Vref, the voltage here is going to be how much? The current in this direction is going to be equal to minus Vref divided by R. So we put an offset here intentionally so that, any critical thing at the transition is not going to be giving us a problem. So, or let me, when we reset this, the output voltage is going to be normally VOS, and VOS is going to be, so let me draw here the voltage. Okay, so let's say this is the case. So the voltage is going to be starting, the time-wise, we might be changing this. So it starts from minus VOS, and then it will be ramping up. Okay, so depending on the initially, this is initially short. Okay, so before this, it is short. S is short. So the voltage is going to be minus VOS. And then the current is going to be generated here. And then the output voltage is going to be, depend on the slope. The slope will be depending on R and C. Why? Because the current is this much, and we know that Q is equal to C times V, and then Q is equal to current times delta T, and that's going to be equal to C times delta V. And then here, the voltage that is critical for us is going to be related with this one and delta T. Okay, so delta V out, the voltage is going to be, since I is equal to, minus Vref or Vref, it's going to be positive voltage anyway. Vref divided by R. Therefore, Vref divided by C times R times delta T. Okay. So since the output initially going to be, with the offset, so offsets are going to be subtracted. And this is the critical thing. And then the counting starts here. Okay. So V out is going to be V out of T and the time scale minus VOS plus 1 over RC 0 to T VRF times dt. The point is that the time where it catches this value is going to be related with your voltage and the final voltage. So if this is V out, and then this one is Vx, okay? So this time is going to be ratio-wise is going to be related with this, okay? So, or another way, Vx divided by Vref, where we try to arrange that RC time constant to be equal to 2 to the power n, okay, 2 to the power n, and this is going to be the time delta t, okay? So this time is delta t. So delta t will be related with 2 to the power n, okay? So because if we select this RC, so that V out is going to be, I mean, if you select this delta t to be equal to maximum delta t, I mean, this is delta t when it's equal to 2 to the power n times t clock time equal to c times r, then things will be related. So the time, the clock time periods, I mean t clock of c times 2 to the power n is going to be related with RC. Then we can find this delta t will be related with this one. So the voltage relation here is going to be related with this delta t, and delta t times the counting TC is going to be our number, representative number. So delta t divided by TC is going to be the number, conversion number, okay? If if the delta t is 2 to the power n TC, then that's going to be the maximum, the number. Okay, so this is a way to make this comparison. So we start the voltage. Here is this circuit here is to trigger the counter, because we don't want to make a mistake here. The counting should start from here, and if you think about like 2 to the power 10, and then that voltage is very critical, and there might be some offsets in there or noise or something. So that least significant least significant bit is so small, is very small, and in order to prevent any mistake in that, and for the last bits, that's why we start this from minus, the voltage starts from minus VOS, and then as soon as it goes beyond 0, this is the 0 volt, if it reaches, then it starts, the counting starts, and then output voltage is going to be like that. And then when do we stop the counting? As soon as V out goes beyond Vx. So the counter is going to be counting when you know, V out becomes 0 volt, the counting starts until the comparator output passes, goes positive. That means that that time the signal is changing. So the number in the counter is going to be our you know, voltage outputs. So the critical thing here is that the result is going to be like, you know, you need to really arrange this 2 to the power n, and the clock should be equal to this. But we should note that this is temperature dependent. Temperature dependent elements. So even if you set this thing properly, the R will change with temperature. So your A to D is not going to be very accurate then, you know. So this is a problem. Okay. So you set this, let's say, to here. This is 2 to the power n, or 2 to the power n times TC. Should be, you know, related to Vref. But that is going to be changing, you know, depending on the value here. So we don't then use this much. So we should do something independent of the resistor changes. The capacitor is not temperature dependent. You know, not much temperature dependent element. So the problem is with the resistor, or, you know, the capacitor might also change. So what we do then is to make that the slope. Slope is determined by RC, and, you know, that's what we don't like, you know. So here maybe I should say that the slope is going to be equal to Vref divided by C. Slope is Vref divided by RC, and the RC is going to be this much, which will be equal to R times C, and that's how we settle the things, the maximum of that. So the solution to this is found using dual slope or dual ramp ADC. Here we again formats or cases. So in the one cycle, we will be connecting this thing to Vx. By the way, maybe we should connect here minus Vx. For this case, it's going to be minus Vx. So we should, you know, take the negative voltage of that voltage that we are trying to find. Some people do this by putting here the reference as the minus, in that case, this, the graph should be on the other side, which is actually better maybe to mention. But anyways, this example here is given this way. So we should use a minus Vx here. So what happens is the switch, we play with the switch first, and then the switch, let me try to draw this correctly. Where does this go from? So maybe I should draw it like this. Let me do it like this. Okay. And then, yeah, so here, this is the point where it will be like that. So this is the reset switch. And then switch 1 should go like this, and then go up and up to here. Okay. And switch 2 should go up here, and then until here. Okay. And then I should be raising this. Okay. So what we do is we first turn the switch, here switch is shorted, so the voltage is going to be resetted. It should be, let's say it's starting from here. Okay. So the capacitor is the voltage across the capacitor becomes 0. So after that we turn switch on, S1 on. So when you do that, this is going to be on. Okay, so this will be on. So therefore there is going to be current in this direction, and the current in that direction, due to that current, the voltage will start increasing. So this voltage increase can be either this way or this way. Okay, so depending on the Vx voltage, because the slope is going to be related with hold on a second, let me understand this first. Oh no, we do the other way around. No, that's correct. So this should be Vx. This should be not Vn, but maybe I should correct this here. I mean, Vn is equal to Vx, so this is going to be Vx. So depending on the value of Vx, there is going to be a slope. So the maximum that it can go is going to be Vref. It can be maximum Vref. It can be either Vref. Okay, we know that Vx is less than or equal to Vref. So for its maximum case, we arrange the RC, and then the time here, Tx is going to be equal to 2 to the power n, again, times Tc. So if we say that this is the after a certain period, wait a minute, something is fishy here. We make the T, what do we do? Tx divided by T. Okay. So there is a confusion here, but T is selected to be 2 to the power n times Tc. So there are a few variations in the implementation. So yeah, I think there is a mistake in the drawing and in terms of scale factor. So this is going to be, yeah, this T is going to be the maximum timing. So this is why it's confusing here. This is T, okay? So the maximum value of 2 to the power n times Tc is this value. So Tx should be less than that, okay? So this is why it's confusing. And you know, the voltage that it goes maximum when Vx is equal to Vref. But if it is different, then you know, it might be less than that. Okay. So here the Vref divided by maximum Vref slope. Okay. Yeah. So normally it should be yeah, something like this, and then quick discharge. Okay. So this should be the actual drawing. So this is going to be 2 to the power n times Tc, and this is the unknown value. So the unknown value will be related with Tx, and this is going to be Tx, okay? And the Vn or Vx divided by Rc times 2 to the power n times Tc is going to be the maximum voltage, and that maximum voltage should be discharged with Vref divided by Rc, because the next time this is going to be the discharge. Let's say the discharge is selected with this color. So the discharge, during the discharge, it will be discharged through here. Same Rc. So the same Rc, and this is going to be times Tx, okay? So the discharge will be depending on, you know, the voltage that's done here. So why is this a change? Because let me just repeat the equation here, because we know that Q is equal to CV, and then that's equal to I times delta T, and that's equal to C times delta V. Okay, and then the delta V1 should be equal to delta V2. Delta V1, where this is the voltage here, this voltage, delta V1, and this is the voltage, delta V2, okay? So the same voltage, but the times are going to be different. And this is the current, and the capacitor is same. So this is the you know, current times here is this one, and then this is the one, and therefore since the capacitors are same, then basically this is what we get: Tx divided by T, or 2 to the power n times Tc, which is called as T, is going to be equal to Vx divided by Vref. Okay, so eventually the ratio of that time is going to be giving us this how much Tc, because the clock is determined here. So the unknown number, the value, is going to be related here. So the good thing here is that the effect of RC is in both sides. Okay, so the RC, R and C variations does not degrade the operation calculation. Okay, so you know, sorry, the slope confused me. You know why this is the case? Because this one, the slope, is the largest slope, okay, maximum slope, and it is constant. And the slope is equal to Vref, because Vref is always larger than Vx. Vref divided by Rc, okay? Here is the slope is smaller, and then the slope is equal to Vx divided by Rc. Since Rc is always, or Vx is always less than Vref, then this is going to be the case. So if, let's say, the number, or Vx, is smaller, for smaller Vx, the slope is going to be constant here, and then this is going to be a smaller Tx, okay? So let's say this is Vx2, Vx prime, and this is going to be Tx prime. Okay, so this is how we make it independent of RC, because currents are same. So we make the control loop, and you know, again, you know, count the voltage where it goes beyond, and then that's how we determine. I mean, of course, we need to have these switches properly operated, and you know, we try to find this value here this time difference is the critical time difference, should be counted. But you know, there is a mistake here, and the you know, this should be the maximum time. I mean, maybe I should put here the scale like this, okay? Not correctly scaled the voltage here, so that's why I was confused a little bit. Okay, so I mean, there are different implementations of this. As I told you, normally, you know, we compare Vx with minus Vref. If you do that, first, I mean, you go to minus voltage, okay, and then fixed like this. This is what it is done. If it is, let's say, a different value here, and the slope is same, so the slope is always same. So slope is Vref divided by RC. This is Vref divided by RC. And then this one is, of course, different Vx, Vx divided by RC. And Vx prime divided by RC, okay? And then the time here is fixed. So this is 2 to the power n, 2 to the power n times Tc. But this one, the other one changes. So, you know, this is if you select Vx here and then minus Vref here. That's the dual ramp dual slope ADC. So we talked about counting ADC and maybe the successive approximation, SAR, ADC, and also single ramp ADC and dual ramp ADC. Okay, dual ramp ADC is simple. You don't need to implement, no need for DAC. Okay, and the other ones, all we used to have DAC, digital to analog converter, to create the compared data. So that's the advantage here. And this is also preferred. I mean, in IC fabrication and IC implementation, that's also preferred. One other ADC that we should mention is the flash ADC. I guess after this one, it's going to be over. So if you want, we can complete this and then you know, stop the course, or we can give a break and then I can give you maybe an example of this algorithmic A to D, which I'm tempted to explain to you how to implement it. Let's give a break and then, you know, meet in 10 minutes. Okay, 12 minutes. Is that okay?
Okay.
Okay. Okay. So Do you see the slides?
Yes, Hocam.
Okay. So one other A to D that you should know for sure is the flash A to D. And in this type of A to D, what we do is we create the voltages, all of them. Okay. So this is like here is the voltage. Now, for this case, we try to shift things. So maybe I should, correct it here. So if you remember, we were comparing the signals. How we were comparing the signals? And we were comparing with up to V least significant bit. But we said that it might be better to switch this here at the half of V least significant bit. So like to go like this, okay? And oops. So this is 1/2 of V least significant bit. And that's better in terms of quantum quantization error. So instead of going into mistake was not going from 0 to least significant bit, 0 to the least significant bit. So the mistake goes from 0 to half of the least significant bit, and then it goes like this, remember? So this was between plus and minus V least significant bits divided by 2. So I mean this is why it's selected as R divided by 2. So if you, let's say that this is 8 volts, okay? So if this is an 8 volt signal, then this is going to be 0.5 volts because of the resistor. So this is going to be 1.5 volt, 2.5 volt, 3.5 volt, 4.5 volt, 5.5 volt, and 6.5 volt, okay? So, and then if Vin is equal to, let's say, this much. So there are already comparators. And then, depending on the voltage here, the result is going to be red. I mean, compared to 5 volt, this is 0.5 volt. So this is going to be 0. So the other comparator will give 0. This one is going to be giving 0. And then this will be giving 0. This will be giving 0. And then this will be giving 1. And this will be giving 1. And then the logic will be converting that to what value? It should be, in fact, the 5 volt should be 1, 0, 1. Okay, so that should be the converted value. This is 0, 0, 0. This is 0, 0, 1. If you think about that way, what is it going to be? Is this correct? Well, this should be correct. There might be 1 bit mistake here depending on the definition, but this is going to be it. I mean, basically, the voltages that we generate to compare, all of them are already here. So T maximum is T clock cycle. So fastest way is here. So in one cycle, you find the result. It's flash. But you know, the fastest way, but not very feasible. Especially for higher resolution. Why? Because as you see here, we need 1, 2, 3, 4, 5, 6, 7. I mean, 2 to the power n minus 1 comparators are needed. Okay, so this is a lot. So this is not really, you know, a good thing. So this is the reason. I mean, we don't use this much, but you should know that, because that's the fastest ADC, and definitely it is one of the extreme cases, of course, but to make an A to D converter. Okay, so again, R divided by 2 is used to reduce the quantization error to quantization less than 1/2 LSB, voltage LSB. Okay, so this is it. I mean, so we have different, maybe A to Ds we have seen. You know, we have seen flash A to D, the fastest, but you know, not so good. What was the time speed of the dual slope A to D speed? We didn't talk about that. Remember, for, you know, increasing and then decreasing, right? Increasing and then there was decrease here. So this was fixed, 2 to the power n times Tc, and this one's you know, something less than or equal to 2 to the power n Tc. So the maximum speed would be 2 times 2 to the power n Tc maximum. Okay, so that's the slowest then, but it saves you an A to D. That's the you know, good thing. And this one is moderate. Why? Actually, we can say that is n times Tc. That was a good one. There's one more here. What is this one? Sigma delta. We will not be you know, talking about that, but that's definitely a very important A to D type. And so we can talk about that or in the graduate courses, but it gives you a good you know, resolution. It is used for high precision devices. Successive approximation, you know, is feasible in this kind of resolutions or bits, and this one is here maybe. you know, but sigma delta is definitely a very important A to D type. And for example, Haluk Hoca's PhD thesis was on this subject, sigma delta type of devices he used for acceleration readouts for accelerometers. So I will not go into that, but I want to maybe add one more type here as the algorithmic, which is not in here. So I want to maybe, you know, show you a different type. Do you have a question up to here? Okay. So there are a lot of different type of A to Ds, and during the break I just added these slides and for you. You know, I like this one, so this is why I wanted to add. The idea here is again to multiply Vn or Vx. I mean, 2 times Vx is compared with Vref. Okay, if yes, then most significant bit is equal to 1. Okay, and then what you do then, it's going to be you subtract the reference 2Vx minus Vref, and then multiply that by 2. Okay, and then compare it with Vref. Yes. If no, most significant bit is 0. Okay, so so the bit number here, this one, let me write it here. Okay, that's what we do for the next bit. If no, no, most significant bit is equal to 0, and then we compare 2 times 2Vx with Vref. Okay. That's how it goes. I mean, it's not nicely written here, but you know, if you do this as we have done in the last hour, you can find the value. Now, this is you know, a way to find this, but we don't need to use voltages. We can also use currents. Okay, currents might be used as the signal. So we can do the same thing here, like I in. Okay, I in times 2. Is it larger than I ref? Yes, no. Yes, most significant bit is equal to 1. No, most significant bit is equal to 0. Okay, the next issue is going to be like this. Let's say the most significant bit is equal to an minus 1. Okay, or b, I guess that's what we were saying, bn minus 1. Okay, so therefore the next one is going to be I in times 2 minus bn minus 1 times I ref. Okay, because depending on this, and then multiply that by 2. and then compare with IREF. If yes, then Bn minus 2 is equal to 1. If no, Bn minus 2 is equal to 0. Therefore, we take this and then, we do again 2 times In minus Bn minus 1 IREF, okay, and times 2 minus Bn minus 2 times IREF. And is it larger than IREF? So we keep reference is fixed, ref signal is fixed, input signal is changed. Okay, so that's the concept. By the way, this is not, you are not responsible. But I thought, this would be interesting for you first to show that there are other devices. And then the second, it is interesting to know that the signal doesn't have to be voltage. So it can be like the current. And this is a totally different maybe approach. So, you create bit cells here. So how can you multiply the signal by 2? I mean, if you use current mirrors, it is very easy. And here, for example, what we do is we take the In current. I mean, of course, Vx divided by something creates In, and then Vref divided by something creates IREF. So you take the current here, and since the gate to source voltages are same here, this In current is going to be like this, In, and this will be In. Therefore, we will have 2 In here. So 2 In is generated, and then, with the help of P current mirrors here, since we source the gate is equal to, we source the gate of this transistor. So the same current is flowing from here. So this current is going to be 2 times In. And here we have Vref, and then that Vref is that voltage is created here. So this is going to be same gate to source voltages. So what we have here is IREF. And we have a comparator, and the comparator output is going to be either 1 or 0, okay, depending on which one is stronger. And how we implement that comparator, I will explain. It's very, very easy, okay? And then, depending on the comparator output, let's say this is going to be Bn minus 1, the most significant bit, okay? So this is most significant bit is determined. And then what we have here as the current, since this is also a current mirror, the same, gate to source voltage, source to gate voltage, same source to gate voltage. We source the gate, so we source the gate same. So therefore, the current through here is going to be 2 times In. And then the current here is going to be IREF. And is it going to be subtracted or not? Will be depending on this value, M9, okay? So if it is, 1, then that switch is going to be on, and the current is going to be subtracted. So this current, which will be again sent to another similar current mirror, maybe double times 2 current mirror, is going to be created. Oops, not so good, but okay. So this current here is going to be 2I in conditionally Bn minus 1 times Iref, and that goes to the next bit. And the next bit is going to be here, is going to be multiplying that by 2. Multiplied by 2 here. Okay, so maybe I shouldn't write it here. So this one is multiplied. Is that clear?
Yes, Hocam.
Okay, so you just prepare this and then put it, next to each other. When you do this, the accuracy is around maybe maximum 6 bits or so. It's very critical if the current multiplied by 2 is this how precise this is done. 2 times IN. So let me, before I go to that, show you the comparator. Comparator is very easy. I mean, if you have signals coming from comparator is this, basically. 2 back-to-back inverters, and then the signal. Let me get rid of this. The device, let me do this. Here is going to be one of the device. Let's say the current mirror. Okay, so remember that there was 2 IN here, and then the other device is this. This is coming from the reference. Okay, and then this thing is trying to push here IREF. Okay, so this is going to be IREF. Okay, so but if one of them is bigger, but the other one is not going to be able to provide the same thing. So if 2I in is larger, if 2I in is larger than IREF, then the current here, the finally, is going to be the smaller one. It's set by the smaller one because the other one cannot set it. Okay, one of them will set. Either this 2I in or this one will set. The smaller will define the current. Okay, if 2In is larger than Iref, then the voltage here is going to be increased so that this will be going into linear region. Okay, this will remain in SAT region. And then, so that the current is determined by Iref. So if the voltage here is, this is going to be, if they are equal to each other, this node is going to be 2.5 volt. But if it is 2In is larger, then in order for the current, because this cannot be larger than Iref, the current here. So, but the voltage here can be increased, and if the voltage is increased, then everything will be consistent, and then the current here, even though here is 2In, this will not be 2In anymore. This will be equal to Iref. Okay, so how can it be equal to Iref? And if this is not in SAT, so this is in SAT. Okay, this is in SAT, this is in SAT, but this is going to be in linear. Therefore, the voltage is going to be larger than 2.5, and it's amplified 2 times. So this is going to be VDD. If the other way around, then the output is going to be 0. So this is how you make a current comparator. Interesting, isn't it? I find it interesting. I don't know. I hope you find it interesting also. So for better accuracy here, because the current mirrors, if they are both in SAT, transistors, they should be in SAT, okay? Because the current, I drain to source is equal to 1/2 Kn V gate to source minus V threshold of N square. Okay, so for the both transistor gate to source voltages are equal to each other, but there is one more term here, and that is this VDS. Okay, so here I in is not going to be equal to I out, because if VDSs are not same. Okay, VDS variations change the result, affects the accuracy. Okay, mirroring accuracy. Because one of them is going to be IN, one of them, VDS is one. So VDSs are different, might be different. So in order to improve that, they decided to use these amplifiers and then fix this always to V bias with the help of this. So this is V bias. So what they did was, of course, they use plus minus voltages and then, use ground here. So it's not ground. Maybe VDD divided by 2 here. So this is maybe minus VDD, and then this is plus VDD. Okay, so the midpoint is selected as the current mirroring here. So therefore, due to the feedback, this voltage is always equal to this value. Okay, so in the current mirrors, always here and everything is same voltage. So VDSs are VDS values are fixed. This is how they improved, for example. Okay. The authors are, I followed their names. in the past, and then I forgot the other. I mean, this is the student, and there was also an teacher explaining that. So they did something else. They said that even if in this case, so threshold of maybe M2 and M3 VTNs might be different, might be slightly different. Okay, so in the current mirroring, if these are also slightly different, then it creates problem. So then, because you want to get more accuracy, and then it's always multiplied. That current, input current is multiplied, and then that creates problems. So they decided to use the same transistor as the current mirror. So what they did was they used switches here, and then the transistor is here. Let's say and this IN comes here, and then during the current mirroring, you store the current in here. Okay, once you set IN here, this gate to source is set, and then later on you make the switching, so IN is isolated here, but then there is this other switch is turned on, and then you use this. Okay, so this gate to source, gate to source is already set. So now this is going to be your I out. So I out is coming from here, and gate to source is already set, and then the gate capacitance, gate to source capacitance holds gate to source voltage. So by doing that, I out is going to be equal to IN. The same transistor, okay? The same transistor is used. So, and by doing that, they can do multiplication of the current. So they put the current in here, and they put it in here, and then I out is going to be IN times 2. So current multiplication can be done like that, and the same devices are used for this purpose. And then dynamic current mirrors are used to multiply the current. Okay, so this was a way, and I did use this ADC in my PhD thesis. Okay, and then and I fabricated the IC version, and then it received first prize in the VLSI design contest in the US. Okay, so this was only a part of my chip, but as you see, I mean, it was an interesting approach I improved it, you know, compared to, you know, these authors. And then I integrated into a system and then fabricated, and then it was operational. So I thought maybe it will be worth to mention about this first, to tell you that, you know, there's a different type of A to D algorithmic. The second, the signals doesn't have to be voltage. It can be current, and the current multiplications can be obtained with current mirrors. And in order to improve the current mirrors, you can either do things like this, fixing the drain to source voltages to a fixed voltage, or another advantage is to, one extra step is to use the same transistor as a current mirror. Okay, so this was the case here. So this is the original, and this is the cycle. It's showing the cycle, how the switch is used to make an input and output. Okay, so this was the idea. Okay, so it took like 6 minutes extra, but I hope it was worth it. Tamam mı arkadaşlar? Any questions? Burada mısınız? Ha, kayboldunuz. Ne oldu? Yemeğe mi gittiniz?
Buradayız hocam.
Nasıl, keyifli değil mi?
Evet hocam.
Vallahi bir tek Zeynep'ten geldi, evet, yani sesi, ama bilmiyorum. Ne diyorsun Mert? Keyifli mi?
Keyifli hocam.
Değil mi? Böyle
Evet hocam.
enteresan yani. Farklı şeyler yapılabiliyormuş yani. Yani ucu açık yani bu konuların. Analog VLSI, hani dijital VLSI da var. Ben kendimi biraz analog VLSI'cı sayıyorum. Çok keyifli, yani keyif alarak yapmıştım tasarımları. Tamam mıyız? Var mı sorunuz? Finalde ne sorulacak falan. Onun haricinde. Final her şeyi cover ediyor. Onu söyleyeyim. Allah, recording'de bırakmışız.